We were yesterday at the, actually there are some questions for yesterday, please ask. But so you want to go to the Variadic Templates. It's a C++ 11 feature added basically because a lot of people were designing libraries in which you have some functionalities that requires 1, 2, 3, or 4 more template arguments, and in order to implement this before C++ 11, you had to resort to macro expansions and very, very, very ugly stuff. So Variadic Templates solves this issue. Basically, you can have a function foo, which is template over a ... t's, right? So you can pass there a list of types. This function then can take these t's and ... args. So this is the syntax you need to use. You put the dots before the t's in the template argument list and before the arguments in the function. That's just a syntax. And you can do also a class. You can define a class A with the same syntax. So that's a template. It's a template class or a template function that takes an arbitrary number of template arguments. What you can do with these args in the function is that you can actually call another function with these args. You put the dots after the args and you expand that list, right? So TS is called parameter pack, and this is called pack expansion. So even in errors, so when the compiler gives you some error messages, it will use this, for instance, it will say pack expansion cannot happen. So this is the official term, let's say. So this parameter pack expansions, args, will turn into something like arg0, arg1, arg2, if there are 3 arguments. So basically, it will add a comma in between the different all the args. And this works also when we do the pattern expansion. When you do a pattern expansion, for instance, you have something like pattern args, you close it, and you put the ... after. So that is not a comma, sorry. That is not a comma, it's a semicolon here. And then you will get the expansion that becomes, like here, pattern arg0, pattern arg2, pattern arg3, right? So you take the old string here, and you take these guys, and you expand them. And you put a comma after each chunk. Similarly, if I want to pass to a function the addresses of the arguments, for instance, I can do like this, a function address of args and ... and this will become address of argument 0, comma, address of argument 1, etc. In C++ 11, they introduced this construct. Yeah?
The question before on the comma separated, the pattern. If the pattern gives an output, how do you retry that? Sorry. For pattern,
Yeah.
if pattern returns something and it's changed, the call, how do you kind of retrieve the values?
The there might be some tricks. One way, so there is not an idiomatic way of doing it, right? But you can use some tricks to do it. For instance, you can, so if all the functions return the same type, let's say integer, you can create an array of integers, and you expand this guy here inside the curly braces, and this will instantiate the values there. And curly braces also guarantees you that these functions will be executed from left to right, so the first, the second, and the third, which is a nice feature. But yeah, there's not an official way of doing it, right? There are ways of doing it. You can also expand using this concept here. So, tuple is a construct that has been introduced in C++ 11. And you can actually, basically do what you're trying to do here very easily if the functions returns different types. So the first returns an int, the second returns a string, and the fourth returns a float or something, right? So you can use this one. And okay, so there is another feature which is the size of ... t. So if I have a variadic template list, if I say size of ... t, this will give me the number of elements in that list. So if I'm passing 3 arguments, size of ... t will give me 3. So there are 3 elements in this list. So here I can create a tuple. And a tuple is a std tuple and the list of types. A tuple is a sequence of, is basically a container of, well, it's not a container in the sense that you can go from the first to the last one. It's like, but it's like a container of elements of different types. So I have a tuple of integers, I have a tuple that contains an integer, a float, and a char, and then I can store values at runtime on this tuple and get those values back. It's very useful. And what you can do here is I can create, I take a sequence of types and I instantiate a tuple with all those types. And I can use a pattern expansion to create a tuple of vector of types. So I can create std tuple of std vector of type t and then expand it. So this will become std vector of type 0, comma, std vector of type 1, comma, std vector of type 2. And I can make it as complicated as I want. So I can actually expand t twice, right? I can a pair of t and vector of type t. And I can expand it. It will be a pair of t0 vector of t0, t1 vector of t1, etc. And I can, if I want my tuple, which is this type here, and I call it data, my constructor can take the expansion of t, so the list of types with arguments, and I can instantiate my tuple with the actual values expanded. Interesting to note here is the fact that this guy, so since the type is here, right? The type is on the class, and here is the type t. This type here, this list of types will be expanded at the time of basically of the class instantiation, right? So if I instantiate b with int and float, I will have a constructor that takes int and float. So we can see here the pack expansion. the pack expansion with a pattern, and then this is called the zipping. I can expand my T multiple times. You have the recursion in action. Here, let's say I want a function which is pretty print. I want to pass the stream that where I want the print to go. Maybe a file, maybe on screen like here. And then I want to print a double char array, an integer, and another char array. How do I do it? Well, first of all, I take my pretty print function, which takes as a first argument an O stream, so a stream where I want to write my output, and then I can implement this like this. I have this pretty print take two template arguments. One is just an argument, and the other one will be an variadic pack. And then the signature of my function takes my string, my O stream, takes the first argument, and then the rest of the list. And then I can say stream output first, and then pretty print with the rest of the values. So it is a recursive call. Now, though, it's not a recursive in the sense, it's not the recursion in the regular sense, because this now will generate another function with a different template list. And at the end, if I don't have any arguments, I just call pretty print only with my stream, and I print new line. What's interesting is that this list can be empty, right? So if in the case in which I want to just print the 3.2, right? I don't want to print the other. When we do std out of 3.2, I will pass the first template argument here, and the list will be an empty list. So size of ts, size of dot ds will be 0. This is still valid, and this is still valid. It will be expanded to 0. The comma will be removed, and this function will be called, right? Yeah. Yeah.
This last thing about the empty parameter pack, does this happen just because I don't have any specialization with just one template parameter?
No. Well, if you have a specialization with one template parameter, it is ambiguous. I think it is ambiguous. We can try. We can try out now, actually. So I wanted to show the code that comes out of the compiler. All right. So compiler explorer again. If you haven't heard about this site, is definitely something to check out. So let's consider now we have our pretty print, and we take our list of arguments, and then we go and call pretty print first with 4 arguments, then with 3 arguments, etc. Interestingly enough, the non-template instantiation are usually before main, and the template instantiation after main. I don't know why. But basically, here you have the pretty print with just your O stream. So it's just a basic function with no argument. And then you have main. And here you can see call of pretty print and you call pretty print of double char const star int and char const star, and with the argument basic ostream, a double and char const, an int and a char const int. So, but this is the function I'm calling now, this function here. And as you can see, it is instantiated here with 4 template arguments, and it does something. It just passed the argument to the stream function. And then there is a call here in this function, call to the same function with pretty print without the first argument. The first argument has already been taken out, and this is here. So the next function is the same pretty print function with 3 arguments now. And inside here, I find basically the same body. Again, this is kind of silly. Why? It's always the same code, right? But then here, I find a function with 2 arguments, and I find it here. The implementation is here with 2 arguments. And here, I call with 1 argument. And then I should find here the call to pretty print with just basic ostream. And this goes to the first one that we saw up top there. So this is actually instantiating multiple functions. So it's not a recursion in the sense that I have one function and I call the same function, or I call different functions, a different function instantiated. What happens if I turn on optimizations? I just don't have any function call. Right? Everything is in line here. I just print the first, print the second, print the fourth. So at the end, if you turn on optimizations, this is what is going to happen.
Where is it that you can see the output of the program? Because here you see the compiler return 0.
Microphone, sorry, yeah.
Where is it that I can see the output of the program? Because here I just have I compile and it says the compiler returns 0, so all good, but I don't see the output of the program.
Oh, you can run the program. You are compiling on your...
I'm using this compiler explorer.
No, you cannot run, I think. You can run?
Okay.
And if you look on the list, the output below. No.
Yeah. Okay. I didn't know that. So, yeah, because okay. No, that's great because they don't want you to run your computation there, but probably for simple thing they probably allow that now. All right, that sounds like free computing resources online. Awesome. We run our stuff. We just drop Dint. We run there. All right, cool. Okay, so now you've seen how this variadic template works. C++ 17 introduces question?
Yeah, thanks.
Sorry.
So is there performance differences from a classic programming with loops, where maybe the loop wouldn't be unrolled so much and remain in the binary even after optimization, and this kind of template programming?
Well,
which probably creates bigger execute.
So the performance differences really, I don't think there are any. You have seen there are a lot of functions that are all in line at the end. So if you turn on optimization, everything is in line. And with functions also happens, but you need to be careful. So there is also link time optimization. So if you have functions in different object files that you are linking, link time optimization can kick in, but I don't know exactly how that works actually. So if everything is in a single in a single translation unit, you probably get inlining, and everything will be optimized out. But yeah, the template, if you think about it, is really simply instantiating functions and objects with some strange names. Right? So if I'm instantiating a function foo with a type t, it's different from a function foo with a type u, and there will be two functions instantiated. So you might think the compiler, you actually can assume that the compiler instantiate the functions, and then it'll end up having some kind of C code, right? So and after that, it will start doing the inlining and everything else. So I don't think there's any performance impact. It just helps you in writing the code in a way that is not replicated, and you can actually you can use templates to create abstractions. Like I want to access my array in a way that is not the standard way, and then through the inlining, you will get exactly the same code that you will have by writing C-style code, but your code look like something else. Yeah?
Just to sort of take something on the...
Mike?
Well, I don't want to contradict anything that's just been said, but you can use these techniques to effectively inline a loop and do by-hand unrolling, which, if your compiler is not obliging, can sometimes be a win. Compilers are often very good at unrolling automatically, but not always. So it's another tool in your tool chest.
Yeah, so you can do, it's right. You can do it in a way that doesn't, so you can manually loop unroll, right? But the code becomes very hard to read and ugly. Or you can do loop fusion by hand, right? You can put everything in a single loop, but then the loop body becomes extremely ugly to read, very difficult to reverse engineer and find out what the bug is. So with this technique, you can keep the syntax clean. I mean, there are ways in which you can do it, and then achieve loop unrolling. You can achieve loop. You can fuse loops and do stuff like that without affecting the user code. I had an example in the previous year. We don't have time to do it now, but basically, when you want to abstract the fact that you have a loop nest. I have a two-dimensional array, and I'm going to apply a function to all points in this 2D array. Instead of writing a for loop on I and a for loop on j and apply my function there, I give my user an interface that says apply this function to all these points. And then inside, I can do loop unrolling, loop fusion. I can do all sorts of things because my user doesn't write the for loops. It is a general rule, I would say, that the control structure of your code, like the loops, should be kept for the performance expert and not for the final user. Or anyway, you want to think about high level when you write your code and then focus on the performance in a separate step. Right? So every time you see a for loop in the main, there might be something wrong. If it is a performance point, if there's a loop that is something that you need, that you care, because it has to be fast, it's better usually to split the control flow of your code from the actual computation. And so then you can take your control flow, and you can actually, for instance, instead of putting for loops, you create a GPU function that just apply this thing to all points. And you can do it because you don't have the for loops at the user code. So one of the major scenes of OpenACC, who knows OpenACC? So OpenACC is a pragma-based approach where you basically take the for loops and you write on top some pound OpenACC. This loop will run on the GPU with this condition and this condition, this condition. This data come from there, data comes from there, and you write it. So it's not part of the language, but it's something that the compiler can understand if the compiler understands OpenACC. And then you put the for loops, and you say, these for loops will run on the GPU. And people like that, but anyway, it is suboptimal because the loop order actually is something that you should care about. So you do for I or for j, or for j for I, which order? It depends on the architecture. And then the compiler will generate a CUDA kernel for you, but then you don't have the control of what the code will actually look like. And so instead, if you do a template thing like this, when you say, apply this function to these guys, then inside you have full control on how you want to run. You can even check what is the layout of the data. You can, and given that, you can schedule a kernel that does something instead of something else. And you have full control on your control structure in the order in which your instructions will be executed. And the order in which the instructions are executed has a strong influence on the efficiency of your code. Right? So C++ 17 allows you to work with templates expansion, with the pack expansion in a more sophisticated way. I'm going very quickly on this, guys. So we have seen here we can take the Variadic template, we can expand it, and basically you get a list with a comma, with a pattern, and you get a pattern with argument 0, comma, pattern with argument 1, comma. But you cannot do, for instance, reduction. So I have all my list of arguments. Can I do some computation out of it? Can I compose these arguments in some way? So what C++ 17 allows you is to specify reduction on the packs, and then you have a unary, it's called unary right fold, unary left fold, binary right fold, and binary left fold. And you can do it with all these operators here, and there's plenty. You can find very clever use of this thing, and by very clever, I mean, wow, who thought this thing did really had a good idea. I will never use this thing because I don't understand it. So for instance, I just show you an example, but basically what you can write, if I have a function that takes the Variadic list, and I want to concatenate my list in some way, I can say, I want to concatenate this guy with string chow plus ... plus, and then parentheses. This is a function. Paren is not here. Okay, this is just a function that put parentheses around, and then I can do concatenate 1, 2, 3, 4, and 5. And what will, so this will be, this just work with the types, so just with the integers. So yeah, the code is pretty, it's not really, I have the code, and we might look at the code. This is just an example, but.
Can you have the int, so you can specify that the template parameter pack has to have all the same type or parameter?
No, you can check it with enable ifs. You can say, enable if all the types are integers, and you write your own stuff, but there's no idiomatic way for doing it. So in this case, it is just integers. I might actually show you the code straight, but.
But you have specified over concat1, there is int .vs instead of type name.
Yes, no, but this is a wrong code actually. This is let me. Maybe it's better if I simply show you the code. Fold expressions. I think this is a make. What did I? CSCS, I guess this is, oh goodness. Yeah, I didn't work these examples. Really, it was just to show you what you can do with this. Let me see if it works. Okay, so it works at least. So here we have this example: concatenate one, concat one, and then 1, 2, 3, 4, 5. And concat one is actually this. I don't remember this code basically. Oh, okay, this is parent. Ah, I see. Okay, sorry, I was confused. This is integer, it's not type name. So this is just a list of integers. Yeah.
So it takes just integers.
Yeah. It takes just integer. No, I was really confused by my own code. So this is like concat with the compile time value 1, 2, 3, 4, 5. Yeah, sorry about that, guys. And this is just integers, so it's a list of integers. And yeah, okay. I thought you were asking, can I check that all my template packs is of the same type? And that is something you can do, but you have to use some tricks. In this case, you know all the sequence will be just values, but they're not types. They're non-type template arguments. And this was to show that you could do also variadic types just with non-type template arguments. Okay, now I understand what I was trying to do, but it's still better to go to the code. So. Here, this parent VS, so parent VS is a function over here that takes an integer value and put parentheses around. It creates a string with this, with just the parentheses and the value in. Just that you see in which order these numbers will be actually made. So, and you have the plus. This is the plus over the string. Oh, okay, yes. If you put the dot inside, so you have plus dot plus. So this is the form. And you can do it with the plus or with the ampersand, with the minus, with the multiplication. This is the idiomatic way of saying it. It's not idiomatic. This is actually the syntax of the language that tells you, or you can do it plus 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 dot 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 plus, or you can do it plus dot dot dot, and you can have different outputs depending on how you are concatenating these numbers. So you can see the outputs here is like plus plus plus. So you do you concatenate in one way. So in one case you have the chow and then the 5 numbers. In the other case, if you swap the number with the string, you get the plus 1, 2, 3, 4, 5, and then chow at the end. Or you can have all the operator first and then the number. So you can have different outputs depending on what syntax you actually use. And I never actually use it in my code because I don't have C++ 17 codes at the moment running. I have only one that just started with C++ 17. But what happens is that when I do this, and with this plus that basically prepend the plus to the 2 operator, I will start expanding these things. So the first one, it become, so I will first do this guy here, would then become this, and then I'm left with this one, and I expand it, then I expand, and I expand. When I'm swapping the numbers and the string, then I will start expanding on the back and do like this. Here is the unary version. When I expand and I get this expansion here. It's actually pretty powerful, but it's not easy. I mean, you need to really try out, I think, for me. At least now, for me, it's not something that I can really use. So you have the binary left, the binary right, the unary left, and the unary right. The idea is that the binary left is that you start from left, right. The binary right, you start from right. When you basically expand, it depends on which one you are actually expanding. So if I'm expanding on the right, or if I'm expanding on the left, I have 2 different behaviors. Right? I expand on the right, I get something. I expand on the left, is something. And with the unary, it's the same. So if I expand on the left or on the right. Well, in this case, so since my operator behaves like the usual one, so you put the plus in the middle, the unary left and the unary right looks exactly the same. But if your operation is not associative, is not commutative, then you get different stuff. So you get stuff happening in different order. Tuples, though, back to the tuples. You have a tuples of vintage. I don't know why they're here, but yeah. So tuple is a sequence of different types, as we've seen before. So I have a tuple of integer, string, and float, and I instantiate with an integer, a string, and a float. Actually, this is not a float. It's a double that will be converted to a float. Or I can simply do auto tuple, make tuple with the list of types. And this is where we said yesterday C++ 17 offers you the ability of construct the class directly with the types by basically automatically generating these functions for you. And there is something else which is interesting, is the fact that how do I get the values out of the tuple? Well, you have the get, You say std get 0, and you get of the tuple, and you get the first element of that tuple. But you can actually get the values of the tuple in one shot by using the tie function. So if I instantiate a char pointer, variable pointer, a variable x integer, and a string str, I say tie ptr x and str equal top, and it will assign these values. So hello will become ptr, it will become a pointer to that hello. X become 42, and the string become word. And this is the tie. So this is how you would do it in C++ 11 and C++ 14 if you want to get the tuple out in a single shot. There are actually references with the tie. I think, yeah, well, but then you copy. Okay. In C++ 17, they introduced the structured bindings, which does exactly the same, basically. Does exactly the same as a tie, in which you can say, assign these values to these variables that I'm actually creating now. So you don't have to create the variables before. You can create the variables in line. So if I have an array of integers, which are 3 and 4, right, two integers into this array, I can say auto x and y with the square brackets equal a, and then x will be equal to 3 and y will be equal to 4. And if I have a tuple, if I have a function that returns a sequence of values, like in this case, I have a function values that basically returns a tuple made of a double, a string, and an integer. Then I do auto, square brackets, the values that I want to get, and then I can basically assign these values to u, v, and w, and then I can print those values with 3.4, hello, and 8.
You can't use directly the map tuple here?
You can, sir?
Why do you need the values function?
Oh, no, it's just to show you that when you have a function that returns something like a tuple, you can use this thing. I show you, this is like the syntax similar to what you get in Python when you want to return multiple values from a function, and you use something like this. And this auto here will be applied to u, v, and w, so there will be 3 different types for these guys. Yeah?
Can we use the microphone more, please? Because in the film afterwards, there's no...
Yep. Promise. Okay, yeah, this concludes the thing, the structure binding. Structure binding was actually interesting. It was introduced at a very, very late stage of C++ 17 standard, like 2 meetings before. And people were not particularly happy about it. But yeah, they actually work quite decently, apparently.